j'ai le grand plaisir de vous présenter Lucia Reining et Francesco Sottile. Alors, Francesco est un brillant chercheur de l'école polytechnique dans le groupe de spectroscopie théorique du laboratoire des solides irradiés. Il est entre autres responsable d'un GDR et il est très investi dans la transmission moderne du savoir à tout genre de public. Quant à Lucia, elle est directrice de recherche au CNRS, elle coordonne ce groupe de spectroscopie théorique. Médaillée d'argent au CNRS, elle vient d'être lauréate du Grand Prix franco-allemand de la Société française de physique. Alors Lucia et Francesco vont nous parler de la photographie couleur d'Edmond Becquerel et de mécanique quantique, grâce à la belle vidéo que vous allez voir, qui a été concoctée par Francesco. Voilà. Alors cette vidéo est en anglais, avec des sous-titres en français. À vous, Lucia et Francesco.
Hello everybody. My name is Lucia.
And I'm Francesco.
And we have been working as a team with our colleagues Matteo Gatti and Arnaud Laurin, a PhD student. We were also interested in Becquerel's color photography. Victor de Sauve, with his thesis, showed us how the procedure of Edmond Becquerel for the first color photography has been tackled, reproduced, and the mystery solved. Our colleagues from the National History Museum had also contacted us to participate in this understanding effort. Our expertise and approaches are, however, completely different. How can we contribute to such an effort? Also, after Victor's explanations, do we still have anything to understand? Indeed, we are theoreticians at the Laboratoire des Solides Irradiés at the École Polytechnique, and we work with theory. We develop equations that we write in form of diagrams. We devise numerical approaches and approximations.
Now, by looking closely to Becquerel's photo, or at least to the plates newly obtained by Victor de Sauve, the team at the National History Museum explained the coloration via the presence of silver nanoparticles embedded into silver chloride. They had to go down to the atomic scale to explain the mechanism of coloration by transfer of electron. But of course, in the microscope, they could see nanoparticles, but not the electrons, which are far too small. The question for us are now, what are the mechanisms for electron diffusion in this material? How can we simulate the dynamics of the electrons? What happens at the interface? To answer these questions, we have to go even deeper at the electronic scale, where everything becomes fuzzy.
We are in the domain of quantum physics. Now, the electrons are not simply described as particles. So instead of talking about the position of electrons in space and time, we talk about probability amplitudes. The probability to find an electron here or there. Moreover, the energies allowed for every particle are now quantized, which means they can only take precise discrete values. Here we have, for instance, an electron occupying its lowest state with a spherical probability distribution. If we perturb this electron by sending light on the system, for instance, the electron can take this energy if it is allowed to jump to another energy state, in which the electron can now have a different probability distribution. We illustrate here different states for the electrons in one atom.
Now, in a real system, in a big molecule or in a piece of crystal, this picture becomes enormously more complicated and the probability distribution difficult to describe. Actually, even the allowed energy levels become a messy affair. Everything is now described by a so-called many-body wave function, a complex object with 3n spatial dimensions, where n is the number of electrons, plus the time. The fact that we have only probabilities is not the only complication. The problem is also that every electron interacts with all the others, and this can lead to collective effects. things that are not just the sum of the effect of every single electron, and that you would have probably never guessed. These collective or many-body effects are found also outside quantum physics. Even in the cinema, in the movie Nemo, lots of little fish can act together to create big shapes, to scare bigger enemies. Exactly like the little fish, the electrons do interact and show collective effects that can completely change the movie.
We don't look at fish, of course. Arnaud, in his thesis, studied electronic properties of silver chloride, and in particular, what happens in silver chloride when you shine light on it. We wanted to know how the electrons would react. So, first of all, we had to translate the dynamics of the electron distribution into mathematical formula. Arnaud really looked deeply into this. So, we have the external perturbation, the light, that acts on the material, here described by this complicated potential. This function chi here describes how the material reacts. It is therefore called a response function. It contains all quantum and collective effects of the electrons. We have now to well describe this chi, create this theoretical machinery to finally have the dynamics of the electrons.
And this was Arnaud's main task, to create a sort of theoretical quantum video camera. Believe me, this was not easy, and Arnaud realized quickly that we had passed him a hot potato. But he did a great job, and today the video camera works. Let's see. This is the first take. We started by neglecting the collective effects. This is a quick calculation, and we are not the first ones to do it for some material. You can see how the electron density moves when we perturb the system. This is a two-dimensional cut of the electron density moving in time and space. You see the atoms of the system, black and green dots for silver and chlorine respectively. This is only the first take, and we know it is too simplistic. Let's now take a more serious one, where we include all quantum and collective effects.
What a suspense! You know, we were the first ones to do this, and we were really curious to see the difference. But what a disappointment! It does not seem that this changes a lot. But wait, of course, the reaction of the material depends on how we hammer on it. The color of the light depends on its frequency, which corresponds to a specific energy. Here we had chosen 2.8 electron volts. We can situate this energy, here the red line, in the absorption spectrum of silver chloride. As you can see, we had chosen an energy range where the system does not absorb a lot. So let us crank the energy up.
Take 3. Haha! Here a lot of things happen. The material reacts violently. If we look at the spectrum, we see that with our frequency we have hit a peak. This indicates that we are on a resonance of the material. This resonance only exists because of the collective effects. Here in the spectrum of silver chloride, it is a special resonance called exciton. I think we are the first ones to look at an exciton in this way. Other resonances exist, and they are analogous to what happens even in classical mechanics. There are famous examples where resonances are hit on purpose or also by chance or misfortune, like the Tacoma Bridge, which was wrongly made to wobble and finally collapsed just because the wind was blowing with a speed that hit the resonant frequency of the bridge. Thanks to Arnaud, we are now able to observe and analyze resonances in the world of electrons.
Well, we brought you quite some way from Becquerel's photo to a quantum video camera to study electron dynamics. But actually, this is how research works. Science cannot be planned. History of science is full of examples in which an activity leads to results in very different fields, like for radioactivity, just to cite an example, still in Becquerel's family. Our contribution is, of course, not as spectacular and important, but it illustrates how we, researchers, may start from a precise question concerning, for example, a mystery in Becquerel's first color photography, and end up creating a very general approach, theory, and numerical tool to describe, analyze, and predict electron motion in real materials.
Arnaud is now tackling the silver chloride heterostructure to study what happens at the interface. But since the method is general, other colleagues are already using Arnaud's quantum video camera to study completely different materials. Matteo Gatti, for instance, is studying what happens in layered systems, using hexagonal boron nitride as an example, while Vitaly Gorelov, a postdoc recently hired on the Chaire Énergie Durable, is investigating a particular allotropic form of vanadium oxide, promising for its properties for photovoltaics.
We do not know where this will lead us in the future. But knowing Edmond Becquerel's broad view and curiosity for all kinds of scientific questions, we are sure about one thing.
Yeah, he would be happy to see that his work has raised questions which have inspired us to make a new little step forward, and so he would approve. Goodbye.
Bye-bye.
Merci Lucia et Francesco pour cette approche originale et ces beaux résultats. Alors, on a une question. On vous demande si vous avez testé l'exposition aux ultraviolets et aux infrarouges. Vous m'entendez?
Oui,
Lucia?
par contre, je pense que cette question était pour Victor.
Ah. Mais c'est peut-être Victor qui pose la question. Bon. Est-ce que Victor peut répondre?
Oui. Non, on n'a pas testé l'exposition aux infrarouges.
D'accord. Merci.
On n'a par ailleurs pas testé l'exposition aux ultraviolets non plus. On a exposé uniquement dans le visible.
D'accord. Bien, merci. Alors, moi, j'ai une question pour Francesco. Parce que je sais que tu fais des actions de médiation en direction des enfants. Alors, est-ce que tu peux nous dire quelques mots de ces actions, s'il te plaît? C'est mon petit doigt qui me l'a dit. Hein.
Alors, je n'ai pas fait encore de vraies actions finalisées aux enfants de façon officielle, mais j'ai commencé à discuter avec d'autres enseignants qui sont à Padoue, en Italie, pour parler aux enfants de l'algorithme, du concept d'algorithme. Mais on n'a pas fait des actions déjà en concertation avec les écoles, et d'autant plus que la dernière année a été très compliquée pour toutes raisons que vous savez. Mais concerne vraiment le concept d'algorithme, un concept qui en mathématiques, mais même en physique, est très important et que ce n'est pas abordé de façon très claire, par exemple, aux écoles élémentaires, bien sûr. Oui. Mais que c'est possible de le faire.
Voilà, c'est une chose importante quand même à montrer aux enfants. En tout cas, bon, on n'a pas tellement de temps là pour d'autres questions, donc je vous remercie encore vraiment chaleureusement, Lucia et Francesco. Voilà, et passe la parole à Alexandre.
Arrête d'appeler sur le multimédia. Tu déranges.
Ah, je voulais quand même... Allô? Non, c'est bon. Il y a quelque chose là.
Merci beaucoup pour cette très belle session.